learn about why do we use the normality assumption. Okay, generally we assume the expected value of ui is equal to 0, and we assume that this is normally distributed, right? So what is ui? Ui is the disturbance or error. Okay, and that is the uh, that error is actually capturing the influence of other related variables which are not included in our model. Okay, so we are assuming that on an average their influence in our model is so negligible that our model will be a best model. Okay, so this ui represents the combined influence on the dependent variable of a large number of independent variables that are not explicitly introduced in the regression model. Fine. Just like we have our classic example, wage is dependent on education. Okay, on education. So there are other factors also which are impacting the wage, but we haven't included them in that model. So that means those variables which have not been included in this model will be affecting the wages, and they will be in the error term. Okay, that influence will be in the error term. So these omitted variables are small and at best random. Okay, so what you're doing is we're assuming that these omitted and neglected variables are small and at best random. This is because when you assume the normality assumption, that is based on central theorem. Okay, so if you assume normal distribution for the errors, then it will be very easy for you. It is easy for us to assume that their sum is going to be normally distributed, and it will help us to proceed with our estimation. Okay, next is this central limit theorem states that even if the number of variables is not very large, or if the variables are not strictly independent, their sum may still be normally distributed. Okay, next is with this normality assumption, when we are having this normality assumption, the probability distributions of OLS estimators can be easily derived. Okay, easily derived. So when you assume the normal distribution for the error term, then we can derive the probability distribution of OLS estimators easily. Okay, because we know that any linear function of normally distributed variables is itself normally distributed, then it is making our job easy. The next is, if you are dealing with a small finite sample size less than 100 observations, then the normality assumption assumes a critical role. Okay, so if we have very few data points, then normality assumption actually is playing greater role. It not only helps to derive exact probability distributions of OLS estimators, but also enables to use T, F, and chi-square statistical test for regression models. Okay, and if the sample size is reasonably large, we may be able to relax the normality assumption. Okay, so basically, whether it is large sample size or small sample size, it is helping us to derive the probability distributions of OLS estimators, as well as the helping us to derive the TF chi-square distribution. Okay, chi-square test for our coefficients. Okay, finally, in large samples, T and F statistics have approximately the T and F probability distributions. So that T and F tests that are based on the assumption that the error term is normally distributed can still be applied validly. Okay. So when you assume the normality of error terms, that is helping us the derive probability distribution of OLS estimators, as well as we can do the hypothesis testing using the TF chi-square test statistics, which will be having the T and F chi probability distributions in large samples. Okay, so that's it for today. I'll see you tomorrow.